I'm Sydney Schultz and I'm presenting a poster on the effect of pH on enzyme activity. Enzymes are globular proteins that lower the activation energy of reactions so that the reaction may occur. They do this by binding to the substrate at the active site of the enzyme. The binding causes the enzyme to change shape, and then that causes a change in the substrate molecule, which then lowers the needed activation energy. Without enzymes, many of our body's chemical reactions would not occur at the rate we need. One of the enzymes that promotes chemical reactions in our body is the enzyme that we've been investigating, trypsin. It's a protease enzyme found in many animals in the small intestine. And it is known that the pH of the small intestine is 8 and that the temperature is 37 degrees Celsius. And when under the right conditions, the enzyme trypsin aids digestion and Our group's hypothesis for our posed question was that the enzyme activity of trypsin would be most optimal at pH 9. So the question that our group investigated was how does the change in pH affect enzyme activity? And our hypothesis was that enzyme activity of trypsin would be most optimum at pH 9, and the rationale for our hypothesis was that in real life situation, i.e. In the small intestine. The rationale for our group's hypothesis was that in a real life situation in the small intestine of a human or animal, the enzyme activity occurs at a pH of 8. So due to the fact that pH of 8 is basic, we presumed that the enzyme activity would be more optimal at an even more basic pH. So the experimental variable of our experiment was the pH of the solution. It was the variable that we were testing. And the pH values that we tested were pH 8, 9, and 10. The control variables, the variables that we remained constant throughout our experiment, was the salt concentration, which was 0.15 molar NaCl, which is the salt concentration in the small intestine, as well as a temperature of 37 degrees Celsius, which is also the temperature of where reactions occur in the small intestine. The negative controls, so for our negative controls, to show no enzyme activity, we added no trypsin to the negative controls. And to make up for the loss of volume in the test tubes, we added an additional 50 microliters of reaction buffer. And as for the actual procedures of our experiment, for step 1, we added 450 microliters of reaction buffer, 500 microliters of azocasein, the substrate, and 50 microliters of trypsin enzyme into each test tube. And the substrate used, azocasein, is a milk protein, therefore absorbs the light best at 440 nanometers, and it's because of the sulfanilamide group contains it. And then for step 2, we incubated the test tubes at 37 degrees Celsius for 20 minutes. And then we added 500 microliters of the 10% trichloric acid, TCA, that's easier to say. And the TCA was added to stop the reaction and precipitate undigested substrate. Step 4, we centrifuged the test tubes at 14,000 RPM for 2 minutes. And the centrifuge reaction after adding the TCA is to remove the undigested substrate. And then step 5, we transferred the supernatant to a clean cuvette. And then step 6, we took the reading on the spectrophotometer. We took the reading at 440 nanometers using a cuvette with DH2O. And then step 7, we read the absorbance and recorded it from the reading at 440 nanometers. We had 3 replicates for each trial, at each pH and each negative control, to reduce variability. Having more replicates would allow us to have more accurate averages, and also a more precise measurement. The bar graph here represents the results from our experiment. So in this bar graph, the x-axis displays the different pHs that we tested, as well as the controls. And the y-axis displays the enzyme activity that we recorded at 440 nanometers on the spectrophotometer. And as you can see, pH 9 had the most enzyme activity, and pH 8 had the lowest enzyme activity out of our 3 variables. And we can pay attention to the standard deviation bars. They represent the amount of variability between the 3 trials tested at each pH. So pH 9 did have the highest activity at pH 9. However, it does seem to have the largest amount of variability. So this slide displays our data in a table format instead of the last slide, which showed a graphical format. So just to run over the averages of our results, like I said in the last slide, pH 9 had the highest enzyme activity, recording at 440 nanometers, which was 0.59. And pH 8 had the lowest, which was 0.399. And our control variables had very low readings, which was expected because they were our controls. And we didn't have enzymes in them, so they should show basically no enzyme activity. As for the standard deviations, like I said, pH 9 did, in the graph, pH 9 showed considerable variability with a standard deviation of 0.102, which was the highest standard deviation that we recorded, which could allude to some possible human errors during our experiment. And as for the t-test results, so we did a t-test from between pH 8 to its control, pH 9 to its control, pH 10 to its control, and then we did t-tests between pH 8 and 9 and pH 9 and 10. The test between the controls shows that our data is significant because they are less than 0.05. And then as for our t-tests that we conducted between pHs, they were both greater than 0.05, which would mean that our data is statistically insignificant. So our hypothesis going into this experiment was that enzyme activity would be most optimum at pH 9. But we initially thought that our hypothesis was supported by our experiment. However, our t-test revealed that our values were not statistically significant, so our hypothesis isn't supported. And another important thing to note is that our values recorded for pH 8 and 9 show considerable variation, as seen by the error bars in the graph. The most plausible explanation for such variability in results would be human errors that we made during our experiment. So after making improvements to our previous design in our first pH enzyme experiment, we believe that the experimental design this time around is more adequate. We focused our experimental variables on 3 different pHs. We also tested 3 replicates of each pH and 3 replicates of each control for each pH. We were able to focus our pH on 3 pHs based off of the results of other groups and our previous trial, which showed little to no enzyme activity with acidic pHs below 7. Based on other groups' data that tested pH, they saw most enzyme activity at pH 9, unlike us, who saw most activity at pH 9. Based off of the results of the group in our class that tested the effective temperature on enzyme activity, they found that enzymes are most optimum at a temperature higher than 37 degrees Celsius, closer to 47 degrees Celsius. So if we were to do this experiment in the future, we could possibly test different pHs at a higher temperature, and we could possibly get higher enzyme readings. We could also use more replicates if we were to do this experiment again, because it would increase our chances of having more accurate results, because we did see quite some variability in the results of our experiment this time. One source of variability in our results from our experiment was seen throughout the second trial that we performed. Trial 2 showed slightly higher results and readings than those of trials 1 or 3. So our average and our variability were both higher as a result of that, and our results weren't as accurate as they could have been. Since our data showed that pH 9 did not significantly increase enzyme activity, we can conclude that the ideal condition to grow bacteria would not be as basic as we previously thought, and that it would not be optimum at pH 9.